Okay, so now we have the people left are diehards, right? I mean, diehard wireless people. It's really Saturday. Okay, so last topic is Mimo. And here's a story. So yesterday we talked about single input, multiple output, multiple receive antenna. We also talk about multi-input, single output, Miso channels. Okay, we talk about things like Alamudi, match filtering, maximum ratio combining, transmit beamforming. All these are essentially Miso and CMO system. So we show that you can get diversity gain and sometimes power gain, but not degrees of freedom gain. Okay, you're not getting any degrees of freedom gain. We already showed that in the high Snr regime, Shannon capacity formula tells us that in high Snr, degree of freedom is the most important thing. So if we want to design a system for a high Snr regime, then we want to get some degree of freedom. But we don't want to go and buy more bandwidth from FCC because that costs us money. So we want to create degree of freedom from another source. And Mimo has a potential to do that. What we want to do today, this last section, is not so much go into details about the transceiver architectures that we do in chapter 8 of the book. But because of limited time there, you just have to go and buy the book and read chapter 8. But rather, I want to focus on this idea of spatial multiplexing. And I want to give you a feel of what types of channel will actually give you this kind of gain. So it's a bit tricky, I think, because in Mimo, you only get this kind of gain in certain environments. And it's important to understand what those environments are. Otherwise, you spend a lot of money building hardware, and you find that the gain is not the one promised to you. You thought they promised to you. But it does depend on environment. So what I want to do is I want to come up with some statistical model which focus on this spatial multiplexing gain. In other words, I want to be explicit enough that I can tell from the model whether I get a lot of gain, so that I can figure out what to measure in the real world in order to get an idea of the gain again. So again, we're following the same approach as the one taken in chapter 2. So we're redoing chapter 2 in some sense, where we talk about wireless channel modeling, but we want to extend that thinking to Mimo channel. And we want to essentially do two things again. We want to be able to connect the physical parameters of the environment and of the device to the performance, and we want to be able to come up with some statistical model. And again, we start with deterministic model and progressive statistical one. That's why in the book it's so important to understand chapter 2, because we're building a lot on chapter 2 intuition to understand Mimo channel modeling. Okay, so again we have this formula. Okay, this is the AWGN capacity. So I extended this formula to the fading channel already. Now I'm going to extend this formula in a different direction, in the Mimo channel. Okay, so in the Mimo channel, let's look at a very simple Mimo channel. So never mind about time variation and frequency selectivity. Let's just fix a narrow band Mimo channel. Let's just freeze time. And we look at this channel. The channel is narrow band, so I can think of the transmit signal at a given time as a vector, x, the receive vector, y, and the receive antennas, a vector. They're related by a matrix H, which measures the channel gains between each transmit-receive antenna pair. And there's a friendly Gaussian noise. Okay, so now what I'm going to do is I'll first derive the capacity of this channel. And then from that capacity formula tells you what is important about this H, which affects the performance, especially in the highest Snr regime. So to do that, we essentially use the trick that we've been using all along. We'll convert this into a parallel channel and compute the capacity of this. So this is another parallel channel. Okay? And how do we do that? We do something called a singular value decomposition. If you have heard of it, great. If you haven't heard of it, don't worry about it. What it is you take a matrix H, and singular value decomposition tells you that every matrix H, whether it's fat or thin, tall or short, can be factorized into a product of a rotation matrix U, a diagonal matrix lambda, and another rotation matrix V star. Okay, so U and V are complex rotation matrix, unitary matrices. Lambda are the eigenvalues, so-called the singular values of H. The values of lambda turns out to be real, okay, and positive, and it turns out to be diagonal matrix, and they're called singular values. So using this decomposition, I can convert my Mimo channel into a bunch of parallel channel, okay? And, okay, so what I do is the following. I take my H, I factorize it into V star, lambda, U, all right? I'm going from left to right here, but that's the way it works, right? So this is the factorization. To convert to a parallel channel, I want to get the channel in the form of the interior, and I want to cancel out the V and the U from the channel. So that's what I'm going to do. I'm going to pre-process by multiplying my data by V, cancel this V star, post-process by U star. These are invertible transformations, just like the DFT matrices. I don't lose any information. So I can now think about the capacity of the overall channel is equivalent to the original capacity. And then, once you cancel this thing, you get a bunch of parallel channel. The ith channel has a gain, which is given by lambda I. Okay? So this is very analogous to what we did for frequency selective channel. The role of I DFT and DFT is played by the U and V matrices here. Same, very similar problem. So now we can now figure out what this capacity depends on. So let's think about this architecture. So what are we doing here is that we're essentially saying that if you have multiple transmit and multiple receive antenna, then I can communicate along the eigenmodes of this channel. And if there are multiple eigenmodes with significantly large singular values, then I can in parallel transmit information per hertz. So for fixed bandwidth, I can now potentially increase the number of parallel pipes I have through this over the air. Okay? So obviously, the whole thing depends on now not U or V, but depends on how strong these singular values are. So the key thing about channel matrix is the strength of the singular values. So if you look at the strength of singular value, I can sort of derive two approximate numbers to give you an idea of how good they are. Number one is, let's focus on the high Snr regime. So in the high Snr regime, what do? In the higher Snr regime, remember our water filling picture. So by the way, the capacity is obtained by water filling over the eigenmodes. You should know by now. I mean, we've done this 10 times already. But let's focus on the high Snr regime because we're interested in the degree of freedom limited regime. In this regime, you can roughly approximate this thing by saying that I'm essentially allocating the same amount of power in all the eigenmodes which are non-zero. Okay? So you get this formula. All right? The capacity is the sum of log of 1 plus the receive power times the strength of the eigenvalue of that eigenmode divided by k, where k is the number of non-zero singular values, the rank of H. Okay? So what are we doing here? We are taking our eigenmodes, we're looking at the non-zero ones, we split our total power into P over K, and we put the same power in each of the eigenmodes, and we get this formula. Okay? So first observation, so now I expand this and I get this formula. Okay, so now let's understand, give some idea onto the performance of this as a function of the parameters of the channel. Okay? Number one is that if I expand this, there are essentially k terms here. At highest and r, each of these terms essentially give me a factor log SNR. So that's my number of degrees of freedom. Remember, AWGN channel, the capacity is at highest and r is like log SNR. So this is essentially giving me k times that, where k is the number of non-zero singular values, which is the rank of the matrix H. So to a zeroth order, the rank of the matrix is the important thing. Okay? The higher the rank, the better the capacity. To a zeroth order. Now, if someone tells you, hey, the rank is the important thing, then obviously this is not going to be the complete story. Because the rank is not a very numerically stable number. I can certainly give you a matrix whose rank is very high, but the smallest singular values are really small. Then it's like telling you that you have a reduced rank matrix. So the rank by itself is not going to tell you the complete story. We need some additional numbers. And of course, if I tell you all the singular values, then that is number. But I want to give some cruder approximation. So the other number turns out to be the so-called condition number. So if I tell you that a matrix is rank k and the condition number is good, then you believe that the rank is a true measure of, in some sense, the capability of that channel. And the condition number, for people who have seen this stuff, is the ratio of the largest singular value and the smallest singular value. So the condition number is very important in numerical analysis because it essentially tells you how well conditioned the matrix is. When you do a lot of manipulation of the matrices, the condition number will show up in the numerical accuracy. That's very key, very fundamental. It turns out to be very fundamental in capacity of Mimo channel as well. So let's summarize. A Mimo channel is one which has good rank and good condition number. That will give you a lot of spatial multiplexing gain. So now we're going to go through a few physical deterministic examples and ask ourselves, is the rank of this channel good? Is the condition number of this channel good? And use that to evaluate when I get the spatial multiplexing gain. So I go to the physical channel now. Let's go back to single input, multiple output, SIMO channel. Okay? And I want to focus on some special cases. And I want to focus on line of sight. So when we talked about fading channel yesterday, we were talking about multi-path fading. So the channel consists of many paths. Okay? Here, I'm focusing on, in some sense, even a more basic situation. There's only one path, and that path is the line of sight. Okay? So I draw this picture. I have a transmit antenna here, single input. I have a linear array of receive antennas. They are spaced at uniform distance apart. Okay? Now, I want to write down what this channel matrix H looks like. In this case, H is not a matrix, it's a vector, where the number of receive antennas is, say, like an R or something. Number of receive antennas n sub R. And let's figure out what this channel vector looks like then. Okay? Now, it turns out that the channel vector looks like this. Okay? The channel vector, you normalize it, it looks like this. So let's understand a little bit about what's going on here, because this is the key to understanding Mimo. This vector is the key. Okay. So let's say I have a zero, let's say I fix this antenna, okay? And what is happening here is that the signal will take slightly different time to get to the different receive antennas, right? Because there's a delay, which is a function of the distance. Okay? Believe me? In a baseband representation, what does delay translate to? Phase rotation, right? Phase rotation. The distances are uniformly separated. So that means the phase rotation is also uniform. 1 theta, 2 theta, 3 theta. Okay? And this is what I'm measuring here. So I start with 1. I have a rotation. And a rotation is always a multiple of this number. Delta times R times omega. What is delta times R times, what is delta R? Delta R is the separation between the two antennas, adjacent antennas, in terms of the unit of the wavelength of your carrier frequency. Okay? So here I'm assuming, I got a question earlier in a break, but I'm assuming a narrow band system here. So the carrier frequency measures the wavelength, and this is measured in terms of number of wavelengths. So in this business, it's always good to normalize it in terms of number of wavelengths. You never want to keep the wavelength unit around. It's too troublesome. So let's understand why this phase rotation increases with delta R. It makes sense, right? Because if I put these antennas further apart, then the delay between different receive antenna will be larger, relative delay, and therefore the phase rotation will be proportionally larger. Okay? And then let's look at this argument, omega. What is omega? Omega is cosine phi, where phi is the angle of incidence. Okay? So let's try and understand why this phi is entering, cosine phi is entering into this phase rotation. We have actually seen this before yesterday. Where did we see this before? Let's see if people remember. This is subtle. Sorry? When we calculate Doppler, we noticed that the Doppler depends on the direction of the path with the direction of motion. But direction of motion is nothing but the same as placing these antennas. You can think of these guys as moving different locations of the same user at different times. So that's why space and time is interchangeable. So this angle, phi, enters into the relative delay between these guys, correspond to the Doppler. It's exactly the same as Doppler. Let's think about that again, in case people forgot. If phi is 90 degrees, what does that mean? That means that these antennas are spaced in a vertical line perpendicular to this thing. Okay? Now this picture is misleading, because this transmitter and this receiver, this transmitter is probably in the other end of the campus. This, I don't know how big this campus is. It looks like a huge campus. Compared to Berkeley, all campuses are huge. And this array is sitting in this room. Okay? So in other words, this distance is huge. And if phi is 90 degrees, if I move slightly on this direction, the distances, what happens? Do not change. And therefore, the phase do not rotate, and therefore omega is 0. So phi is 90 degrees, omega is 0. If phi, on the other hand, is 0 degrees, that means this array is aligned with the line of sight. That is the maximum change. So therefore, omega is largest, is 1. Okay? So as a function of omega, as a function of the angle of incidence, omega changes, and this entire vector changes. And this vector is the basis of telling direction. And that's why this antenna array can sense different directions, because the signals coming from different directions are now creating a different channel, so-called spatial signature, onto my impinging on my array. Because different directions translate to different phase rotation. And that's the basis of telling direction. Okay, so I'm in some sense going more detail into the beamform picture in my last section. Okay? And that's it. That's the idea. Okay, so we have to understand this idea. And that's why I went through a little detailedly, because I'm going to use these beamform pictures like don't know tomorrow from now. Is there any question about what's going on here? Okay. All right, so this is the received spatial signature. And so if you think about processing, okay, what do? If I want to do optimal processing, what's the optimal processing here? Do we remember? Sorry? Co-phase combining. Co-phase combining. Match filter. Co-phase combining means what? I multiply by the conjugate of this vector, and I get a power gain of nr4, where nr is the number of receive antenna, because I'm adding 1 plus 1 plus 1 plus 1. 1 plus 1 equals to 4. Hey, good. I'm reinventing elementary school mathematics here. 1 plus 1 equals 4. And I get a 4 and 2 dB, 3 dB for power gain. Okay. So that's what I'm doing. I'm co-phase combining, and that means what? That means by changing this vector, I'm essentially combining signals from different directions. So if I figure out that the transmitter is in this direction, then I will change my receive vector to point towards that user. So that's the beam. That's the beam. Okay, so we do the same thing for Mimo. Line of sight, exactly the same reciprocal situation. I do transmit beamforming now. So the transmit vector is this one. Again, it's a function of the angle. Same thing. So here, I do transmit beamforming. I can get NT for power gain. I do co-phase addition at the receiver by pre-adjusting the phase at the transmitter. Okay, so here's a question for you now. I have a transmit array. I have a receive array. And there's a line of sight environment. Separation is D again. This receive array is in this building. This transmit array is on the other end of campus. Okay? 1 kilometer away. How many degrees of freedom do I get from this? So I have, say, NT transmit antenna here and NR receive antenna here. How many degrees of freedom do I get? Minimum of NR-NT. So let's think about it. What does degree of freedom mean? Degree of freedom means essentially the rank to a zeroth order, the rank of this matrix H. All right? Think about the rank of this matrix H. So think about the signal that is sent from each of the transmit antenna impinging on the receive antenna array. This is the column of, this is each of the column of this matrix H. Okay? So let's use the whiteboard here. Okay? So the channel matrix H, I can write it as H1, H2, H, and T, where each of these guys is the spatial signature of the ith transmit antenna. Okay, so each antenna, each transmit antenna is creating a signature onto my receive antenna array. And if I want to look at the rank of this matrix H, then I have to figure out how many of these guys are linearly independent, obviously. And how many are linearly independent? Don't be shy. 1 is linearly independent. This is a rank 1 matrix. Why is that? So remember, what is the spatial signature of a transmit antenna given by? We can look at this formula again. So that's why I want to make sure people understand this formula. The spatial signature is a function of delta. Oh no, let's draw the other picture. This picture is better. The spatial signature from a transmitter to a receive array is a function of delta, the separation, that's fixed. That's the same for every transmit antenna. And it's a function of omega, which is a function of phi. So the question is, do these transmitters come from different directions or the same direction? What do you think? Same direction, right? This distance is 1 kilometer apart. This separation is 1 centimeter apart, to a few centimeters apart. So they come from the same direction. Right? So therefore, this matrix is rank 1. In fact, you can write out explicitly what this matrix is the outer product between the transmit vector and the receive vector. Rank 1. And so what do we get? We can do a transmit beamforming. We can do receive beamforming. So actually we can get an NR times NT full power gain, but we don't have any degree of freedom gain. Okay? So let's draw a picture. And now we can go to beamforming picture. So let's go back to beamforming again. So what is the beamforming picture here? When I say beamforming picture, when I draw this thing, what am I really drawing here? I'm basically drawing the following fact. If I fixed a receive vector, so that means if I fix a receive co-phase combining, a particular omega naught, that means I am combining signals from different directions differently. And the direction that combines the best for me is at omega naught. In this example, 90 degrees. So I'm pointing a beam at 90 degrees. So therefore, at this point, the signal strength is the maximal. Okay? As I move away from 90 degrees, then the projection of the received signal onto my fixed combiner is reduced because I'm not doing co-phase addition anymore. It's weakened until after a while it gets reduced to 0. And that's here. As you circle around, that's what I plot. So I plot exactly the dot product between my receive vector, that is the direction I point to, and the impinging direction is a function of omega. The dot product is what I plot, and that's the beamforming pattern. So that's exactly mathematically what the beamforming pattern is. It's a dot product between my vector and your vector. Well, with my vector, I focus on a certain direction. Your vector, I span around 360 degrees. Okay? So this is all normalized, right? So this is 1 here, and it reduces to 0. Okay. All right. So what does the beamforming pattern does? It gives the antenna gain in different directions. Okay? It's saying that if I point a beam in a certain direction, it tells me that if the signal comes from another direction, how much energy, how much signal is projected on. Okay? All right. So let's use this beamforming picture that we have to understand why in the Mimo case, with a line of sight, we don't get any power gain. So here's the picture. I have a transmit array, receive array, with one line of sight. Now, I want to point so now what's the optimal communication strategy? Well, the transmitter says, look, the receiver are all in this direction. Let's point a beam to it. Remember this picture. This arrow is 1 kilometer long. This separation is centimeters long. You have to remember that. I can't really draw it like that, but that's the thing you should think about. So I'm pointing a beam in this direction. I say, oh, yep, that's where the receiver is. I want to focus my energy there. Okay? This gives me a NT full power gain, because now I'm not wasting my energy to all directions. I'm focusing my energy into one direction. Okay? That gives me NT full power gain. The receiver says, oh, I know the transmitter is coming from that direction. Let me point a beam in that direction to make sure I maximize the energy I absorb from that direction, my sensitivity to that direction. Okay? So together, you get an NT times NR full power gain. So energy is focused along a single beam, but it's still not a degree of freedom gain. Okay? So it's not a degree of freedom gain. So how do I get a degree of freedom gain? Let's think a little bit about it. If I want degree of freedom gain, essentially, I need to do something. One thing I can do, a thought experiment, is, well, maybe I can pull these antennas apart. So the problem is that the antennas are too close together. So from a long distance, they essentially look like a single point to me in a single direction. So now, what I'm going to do is I'm going to perform a thought experiment by pulling these two transmit antennas far apart. In practice, of course, it's hard to do because these guys are co-located on the same device. But now you have to build a device which is half a kilometer large. Because the distance is like 1 kilometer. So you want this distance to be comparable to this distance so that the two angles are now completely different. So now the channel matrix H will have two signatures, H1, H2, which now look very different because they come from very different angles. Okay? So now I have a rank 2 matrix. Okay? So I have a rank 2 matrix. And now I have 2 degrees of freedom. This guy can send signal at a certain direction. The other guy can send signal at the same this direction. And they come from very different direction. And so I can simultaneously listen to them. Okay? So I get 2 degrees of freedom, rank 2. Okay. Now, let's think about how we can simulate this in a situation where the transmit and the receive antennas are co-located. Okay? So now, I'm back to the situation where the transmitter and the receiver are on the same device. Okay? And this is where multipath comes into use. So multipath was a bad thing before, but now we see that it will become useful. Why? So my transmitter and receiver is at 1 kilometer apart. These antennas are very close distance apart. If I only have the line of sight, then all I can do is to form beams and focus my energy along this direction. Okay? Now, there's another path which is reflected off a wall. What can I do? I can form another parallel beam along that path. Right? As long as these two beams are far enough apart, because the angles are very different, then I can simultaneously transmit signal on the two beams and simultaneously receive signal from the two beams. And this is the whole story under Mimo. This is the Mimo story. Because this idea of having two transmit antennas very far apart and be able to distinguish the receive antenna array is not new. This is known a long time ago in array processing literature. For example, if you have two users in a network, and you try to build a system where you can simultaneously listen to the two users, you can do this. What Mimo brings to the table is that they notice that, multipath, you can get the same effect even when these transmit antennas are co-located on the same device. And this is the picture. Okay? So a scattering environment essentially allows us to have multiple degrees of freedom even when the antennas are close together. Okay? Now, this is a picture that we should ponder on a little bit more. And the reason is that this picture essentially tells you how multipath was turned from a foe to a friend. So let's look at this picture in a case of a single transmit, single receive antenna. Okay? So if I have a single transmit, single receive antenna, what happens? Okay? So, what's happening here? If I have a single transmit, single receive, and I have multipath, same environment, what's the beamform pattern that is formed by the two antennas? Do you remember? Silence. What's the beamform pattern? Omnidirectional. Right? So multipath, is it a good thing or a bad thing? It's a bad thing now, right? Because if there was a line of sight, then I receive the signal. But if there's another path, then because I have an omnidirectional antenna, I can't tell them apart. It's just two signals arriving my antenna. And they'll add up together, and they may destroy each other. And if they destroy each other, I'm in a deep fade. Bad thing. Now, suppose I start adding receive antennas. Here. Suppose I add a bunch of receive antenna now. I have a receive antenna array. Still single transmit antenna. Now, I can form beams one this way, one this way. Because now I can form beams. And forming beam means that now I have resolution. So mode diversity is all about resolution. It's about the fact that you can resolve into the system. So before, we were confused because we have no resolution. We have no angular resolution. We can't tell the signals come from different directions. So that when they destroy each other, there's nothing we can do. Okay? So this is analogous to the delay resolution that I talked about earlier. So I have a narrowband system, so I have no delay resolution. I have a single antenna, I have no angular resolution. They destroy each other. Now I'm going to give you angular resolution. You can now form two beams, and now you can tell the two paths apart, and you get a diversity gain. And now you're crawling up to an AWGN channel, back to the line of sight channel, closer. Okay? Now, if I give you an antenna array here as well, then you're going beyond AWGN channel. Because now, this guy is also capable of forming beams like this, and therefore he can now send two independent streams of traffic. And that will give you a Mimo spatial multiplexing effect. So this is the picture that one should keep in mind when one thinks about why multiple antennas can be turned from a foe to a friend. But the key insight here is that the Mimo is essentially coming from the fact that multipath gives you a different angles and therefore provide you with parallel degrees of freedom. Okay? Now, is that point clear? Any question? Okay, so let's go on to a deeper point. Since this is the end of the course, I'm not going to deeper stuff. So now one can start asking yourself, okay, it seems that then the more multipath there are, the better. Yeah? In fact, if I don't have, can you multiplex many streams of traffic in parallel as the number of multipaths increase? Okay? Okay? No, right? So multipath increasing is like saying that the rank of the matrix increases. Right? It's increased from rank 1 to rank 2. Add one more path, becomes rank 3. But the rank, as we said earlier, is not the only important thing. What is another important thing? It's a condition number. And as we add more and more paths, at some point, the condition number will go bad. So even though artificially the rank seems to be increasing, the condition number will go bad. So now we want to figure out when does this condition number go bad. And that will limit us in terms of the performance gain. Intuitively, when the angular separation of the path decreases, when the paths become close together, so close that the condition number will get worse. And that put a limit. So in some sense, I have an angular resolution, and that limits me from the spatial multiplexing gain. Now, so if you go to this picture, then let's look at what the condition number is. Okay? The condition number is basically the rank of this matrix, the condition number of this matrix H is obviously a function of how closely aligned these two vectors are. If H1 and H2 are identical vector along the same line, then the condition number is 0 or infinity. So the condition number is a function of how closely aligned they are. Okay? And in fact, the condition number depends on these two things. The dot product between the signature of omega 1 and omega 2, where these two are the directions. What is this quantity? This is the beamforming pattern again. So the beamforming pattern not only tells you the antenna gain in different direction, it tells us about angular resolution. It means what? It means that if I form a beam in this direction, and there's another path coming in at a different direction, then whether or not I can tell them apart depends on the projection of that path. In other words, the value of the beam at that angle. So from this picture, what is the key property of this beamform pattern that tells us about the angular resolution? It's the size of the beam, main lobe of the beam. If the main lobe of the beam is very narrow, then what does this say? It says that as long as signals from different direction, slightly different direction, I can tell them apart because I have very good angular resolution. So the key parameter here is now the angular resolution, which is the width of the beamform pattern. So now we want to know what limits the beamform pattern size. So we do some plots, okay? So here's a plot of how the beamform pattern's main lobe width, beam width, is affected by the physical parameters of the problem. So this is an example where the antenna array has 8 antennas. So let me okay. So the picture is the following. I have an antenna array. I put the antenna, I put 8 of them on my array. I put them at lambda over 2 apart, so half the wavelength apart. LR is the total length. Okay? So delta R is half here. All right? So this is the first picture, the one on the left. In the second picture, I'm doubling my entire size. I'm adding 8 more antennas. I'm keeping them separation at lambda over 2. And now I have 16 antenna elements. And this is the beamform pattern. Okay? So the beam width is reduced as I increase the number of antenna elements. This is very intuitive. Why is this intuitive? Because the bigger my array is, the more sensitive I am to directions. Remember, the sensitivity of direction is given by what? It's given by the delay, the relative delay between signals arriving at different antennas. If I have a bigger array, then I'll just be able to magnify the relative delays, and therefore make me more sensitive to different directions. Therefore, a narrower beam width, and therefore better angular resolution. Okay? Now, let me ask you a question. Suppose I don't do this. Suppose I say, you know what? I have a device size limitation. So I can't double this to 16. But what I could do is I have no hardware limitation, so I can buy 16 antenna elements and all plug it in into the same amount of space. Okay? Do you think the beam width will be reduced or not? No, right? Because I'm not really increasing the sensitivity. I'm in some sense oversampling the signal. So this is the picture. This is the case when the separation is lambda. So going from lambda to lambda over 2, your beam width looks much better. Here, you cannot even imagine this is called a beamforming pattern because the lobe is like huge. At lambda over 2, you get this beam. At lambda over 3, you get this beam. At lambda over 1 over 16th, you get this beam. Okay? The beam width never reduced beyond lambda over 2. Okay? That confirms our intuition. Now, the beam width is actually, you can compute that. If you keep lambda over 2 separation, the beam width is roughly 1 over L, where L is the length of the antenna array measured in terms of wavelength. Okay? All right, so we can now answer the question. The channel H will be well conditioned if these two angles is much bigger than 1 over L. Okay? So in other words, you have the two beams, okay? You have the two beams as resolution. Let's see, what am I trying to say here? So if you go back to this picture, okay? If we go back to this picture, all right, then what's the picture? The picture is the following. If I have two paths coming at an angle, which is separation, which is larger than 1 over L, the width of the beam, then I can tell them apart, and I can create my two parallel channel. As I increase the number of paths, the angular separation will become less than 1 over L, the width of the beam. And then I can't tell them apart anymore. They don't provide any significant increase in degrees of freedom. Okay, that's the picture, and that's why the resolution is important. So now, let us answer the question. So I'm going to skip some slides here. We're getting a bit late here. So let me go to the main point here. Okay, so now we can ask a question. Okay? How many degrees of freedom are there in a given channel? So I'm going to focus on a specific model to answer this question. So the model I'm going to use is the following. It's really an indoor model, typically. So in an indoor model, you typically have clusters of scatterer in your environment. Maybe a clutter of objects, a wall there, and so forth. Okay? So I'm going to model them as clusters. And in the cluster, there will be reflection and scattering and so forth. Okay? So now I want to know how many degrees of freedom are there in this channel. How many parallel streams can I send in this channel? Okay. What does it depend on? What are the key numbers it depends on? First, it certainly would depend on the angular spread of the multipath. If the multipath are all sort of in a very narrow direction, then I don't have the spatial multiplexing gain that I had earlier. Okay? So it depends on the angular spread. Number two, what should it also depend on? Let's look at this picture. So I have, let's say, one cluster to simplify the story. Okay? If I have a certain array size L, then I can form, say, two beams, two parallel beams onto this object. Okay? If I increase my array size, the beam width becomes narrower. And now I have better resolution. I can now form, say, 3 beams into this object. I can now create 3 independent paths. Okay? And I get a Mimo gain from this to this. So therefore, how many beams can I form in parallel? Well, if the angular width of this is omega, the number of beams I can form in parallel is roughly omega divided by 1 over L. So therefore, one can actually show that for a large antenna array size, so that we don't have to care about fractional effect, the degrees of freedom is minimum of the product of the antenna array size times the angular spread. Okay? So this is a nice formula. So this is a thesis of my student, Ada Poon. The degrees of freedom is the minimum of LT omega T times LR omega R. This formula gives me the degrees of freedom gain as a limitation, as a function of both the device parameter and the channel parameter. What is the device parameter? The device parameter is L. It tells me that if I increase L, I get a linear increase in degrees of freedom. The channel parameter, the environment, is given by the angular spread, the total angles that the clusters of scatterers subtend the receiver. Okay? And this is omega T, omega R. And the product gives you the total degrees of freedom. Does this formula remind you of anything? So anyone who's taken signals and systems have seen this kind of formula. Time bandwidth, right? So this is the spatial analog of the time bandwidth formula. Okay? So here's the analogy. If I only have a single antenna, then if I transmit over t seconds over channel bandwidth W, I have WT degrees of freedom. If I add a spatial multiplexing capability, Mimo, with an array size L, with a channel with angular spread omega, I get L omega spatial degrees of freedom per second per hertz on top of the WT. Per WT, per second per hertz, I get L omega degrees of freedom. Okay. So, all right, a lot of stuff here, but let me just conclude. Okay, so what's the current situation here? Let's say a few more words about that. So, so Mimo essentially is important in essentially two situations. One, in an indoor environment, okay, with high SNR and rich scattering. So in the indoor environment, where the SNR is high and the scattering is rich, a lot of scattering, then Mimo makes a lot of sense. So that's why we see Mimo appearing in Wi-Fi products, 802.11n standards, emerging standard. This standard is always emerging. It's been emerging for many years now. It's still emerging. Okay. Cellular is a bit tricky. Okay. Users have wide range of SNR, and sometimes the angular spread is not so great in outdoor environment. And that's why people are a bit more tentative on applying Mimo into cellular systems. People are still thinking about it. Okay? But sometimes because of market pressure, you have to build new products with high capability. Mimo is becoming, adopted as well. But not necessarily because of the performance gain, because of marketing value. Okay. So here's a question I want to ask. When I talk about dumb antennas, I said, look, information theory tells us that if you have a fading channel, if it has fluctuation, you can exploit it and get performance gain. Then dumb antenna is a way of inducing that artificially. Okay? So now we follow the same idea, which is if there's limited angular spread in nature, how do we artificially or induce this angular spread so that we get degree of freedom gain? I'll give you two ideas. These are very tentative ideas, of course. Okay, one idea is you can do spatial division multiple access. So instead of doing Mimo, you think of these guys as different users. Now the angular spread is pretty good. Okay? So another approach is the following. Okay? Suppose you have Mimo handsets. You want to advertise a good system. You have Mimo handsets. I have a base station. Okay? The base station may not have Mimo, doesn't matter. But unfortunately, the angular spread is limited. So therefore, the point-to-point communication to this Mimo device has a low capacity, low degrees of freedom. The angular spread is limited. What I could do is I could induce those degrees of freedom by having these base stations cooperate, forming a giant macro array, and then they can cooperate to send to this Mimo device, or this Mimo device can send to it, and they combine information and receive it. So now, the angular spread is much better because these base stations are distributed. So now I create angular spread from no angular spread, or from limited angular spread. Another possibility, so this is you can think of this as infrastructure cooperation. You're joining up these base stations and cooperating, infrastructure cooperation. Another approach is you can do user cooperation. So now I have a Mimo link, but there's only a line of sight. So no degree of freedom gain. Now, other of my friends can act as relay, and therefore they can artificially, in some sense, become a scatterer and transmit my information to the receiver. And therefore, I have artificially increased my angular spread. Another way. Okay? Conclusion. So modern wireless communication says fading should be exploited. We gave you two ways. One, fluctuation. Two, degrees of freedom. If you want to implement that in real systems, you really need to work the theory into the system issues. Okay? And what we did here is to suggest that, given this point of view, in some cases, when fading is not there, you can try to induce it by appropriate system design. Okay? So that basically concludes my last section, Mimo. All right, thank you.